Hello and welcome to video 3 on this intro to Python language using Spider. This is the final video. In this one, we're going to use our data set and look at a scatter plot, run a correlation, look at a simple ordinary least squares regression or an OLS regression, and then run a multiple OLS regression. So previously we imported our data set, we ran a bunch of different descriptive statistics information, and then conducted a independent samples t-test. Now what we're going to do is we're going to answer questions about the relationship between two continuous variables. So here we're going to try to determine the relationship between GDPPC and corruption reverse coded, leaving corruption on its original metric from 0 to 10. The most basic graph for two continuous variables is a scatter plot. The scatter plot will show us that the two variables appear to be related. We will follow this visual inspection up with two tests. First is a correlation to determine how tight the relationship is between the two variables. A correlation close to 0 means that there is no relationship, essentially an amorphous blob. A correlation close to 1 or negative 1 indicates that the relationship is very close to a perfect line, either positive if it's 1 or a negative relationship if it's a negative 1. Next, we're going to then run a regression to look at the nature of that regression or that line of best fit. And this line is going to be defined by a slope and intercept. And the regression output will tell us if either of those are significantly different from 0. So first what we're going to do is look at the scatter plot. So we're going to essentially take each value of GDPPC on the y-axis and the country's corresponding corruption 2 on the x-axis. So we're going to use our df complete. So we have our x and our y in 289. We're going to give this plot a label. We're labeling X as perceived corruption, labeling Y as gross domestic product per capita, and then using this as show. We're going to highlight all 4 lines of code and then run that together. So looking at this, we have potentially a floor effect, a lot of low values here as corruption is really high. We have this potential outlier here. So we may want to remove this case and run the regression both with and without it. But looking at this, we can imagine a negative line going between there. Next, we're going to run a correlation, which is a measure of association, sometimes called Pearson product moment, or Pearson R. The sign indicates the directionality, so it's going to be positive or negative. Now, correlation does not specify causation because this is cross-sectional data. So what I'm going to do is we're going to go ahead and use df complete, our first variable, dot core, then the next variable. So when we run this, we get a correlation of negative 0.89, which is a strong negative relationship. Next, we're going to go ahead and run a regression. The regression provides additional information about the relationship of two variables. Specifically, it allows you to guess what value of one variable is given the information of the other variable. Here, we will regress GDPPC, our dependent variable, over corruption 2, which is our independent variable. First, we're going to specify the model, saying, okay, we're going to store the results as model fit. We're running an OLS. Let me write in our equation. Our equation is GDPPC regressed on corruption 2, provide our data frame, and then dot fit is going to give us our regression fit statistics and information. We're going to run this, storing it as an object, and we're going to go ahead and print the summary for model fit. Let me go ahead and expand this a little bit. And this provides the OLS regression results. We have our dependent variable. Our method is OLS, ordinary least squares. Number of observations, because we are using that reduced data set. Our degrees of freedom. Our covariance type is non-robust. Our R squared, and just R squared. So as you include more independent variables, we need a control for potential bias, so you probably want to interpret adjusted R squared. We have our omnibus regression test. That's our F statistic and a corresponding p-value. It is statistically significant, so we're accounting for a statistically significant portion of variability. Specifically, approximately 80% of the variability in GDPPC could be accounted for by perceived corruption. Of importance, though, is our intercept. So know nothing about a country's corruption. Our best guess is 39,300, and so forth. So we do have scientific notation here. We have our standard error and our t-value, and this is statistically significant. This is our upper and lower bounds for constant intervals. For each unit increase in corruption 2, so as countries go from a 3 to a 4, a 6 to a 7, and so forth, there is a 4,761.49 reduction in GDPPC for each unit increase. We're also going to run this a different way. So in 202, we're going to use line regress, our IV and our DV, and we're actually going to go ahead and store slope, intercept, R-value, P-value, standard error. We're going to extract that information. We're going to create a function called predict. We're going to create a line of best fit. So based on the slope, intercept, and x, we're going to go ahead, and x is going to be filled in later by corruption 2. We're going to return our predicted score. So what's on that line of best fit? So we're going to put this as fit line, and our predicted values based on that regression. So again, this is y equals mx plus b, so y hat, our estimated outcome variable, is an equation of our intercept plus our slope, or coefficient, times unit of x. So now we have our predicted values. And now we're going to go ahead and visualize that relationship for the line of best fit. We're going to go ahead and use that same scatter plot. And we're going to go add a line of best fit called fit line, making that R, add our labels, and show the plot. So this is our line of best fit from that regression. We can also extend this into multiple linear regression. So I'm going to create an object called model fit2, and I'm just adding a plus literacy. So I'm including another predictor of literacy into our model. And now I can interpret our regression. So we're using all the same information here. Our R squared adjusted is now about 68% of the variance of GDPPC can be accounted for by the model. We have our intercept and our slope for each unit increase now, rather than the larger amount. It's now a reduction of 3,500. And for each unit increase in literacy, GDPPC goes up by 95 points. And all those are statistically significant. So before we conclude this video, I do want to mention there's a large Python user community, so it's relatively easy to find materials, example code, and solution to your Python problems online. As before, you can also use things within the documentation and do like help numpy. Actually, looking at this, I'd forgotten we put numpy as np. So if we do help np, there we go. And that has the documentation associated with it. There's also things like docs.python.org, has tutorials, reference setups, the whole 9 yards in there too, and has more information. Now, if you don't want to install Anaconda, there's other distributions such as Canopy and WinPython, and you can also use things as Jupyter Notebook, which is a different interface of running Python code. I also want to mention, though, be aware of different versions of Python. There are some differences between Python 3 series and Python 2 series. As a result, some of the old Python 2 might not run on Python 3 and vice versa. Many prior Python users still prefer Python 2, but most new users are starting with Python 3. Which version to use is your choice. It will not make much of a difference. However, there is no more support for Python 2. So I do want to mention that. I hope this was helpful, and enjoy coding.